Welcome back, everybody, to another fun episode of Science Matters, or What Matters in Science, depending on how you want to look at it. So, today I wanted to talk a little bit about how science is really supposed to work. So, there's been a lot of criticism by people who I don't really think understand how things work, sort of on the academic side or the national lab side, or how they should work in the general scientific community side. It's not always how they actually do, but how they should. And I think that's the important part because sometimes things don't always work because humans are humans and scientists are human and therefore always prone to error. But error correction is supposed to be part of it. We're going to get to that in a second. The peer review process. I caught a bunch of stuff in comments this week because there was an article that was completely kind of debunked, or at least in the process of it. And a journal came out and kind of outed itself for making a mistake. It was the astroparticle physics. Um, Big long story. It's episode 2 of the show. You want to go watch it, please feel free to. But I wanted to talk about the peer review process in general. So when you're a scientist, one of the things you're signing up for is to accept criticism and absolutely accept criticism. Now, what do I mean by criticism? So if I put forth a theory and I'm trying to prove that theory with an experiment, I expect people to try to rip it apart, not just with pseudo-scientific babble. Okay, not which going, I don't believe that's true. You can't, that's not what we're talking about. What we're talking about is people who come at it and say, I'm not sure that's true for the following 6 reasons. And then they list those reasons out and they're rational, they're well thought out, probably coming from other scientific perspectives of saying, hey, look, that violates this law that won't work because of, XYZ. Oh, that's already been done or already been proven or already been disproven by somebody. All those are important criticisms. And all those things do happen. And the peer review process is in place so that when you come up with a new concept or you come up with a paper or an observation or an experiment, you send it into a journal to be published. They're going to send it out for peer review, which is supposed to be an anonymous process, and usually it is. Sometimes it gets outed, but and sometimes you can kind of figure out who the reviewers were. Anyway, it's supposed to be anonymous, and the reviewer's job is to say what's wrong here. Hey, I did this experiment. This experiment showed here. I'm like, well, yeah, but you forgot, this one fundamental flaw in your experiment is this, which has happened. Like I had a friend who was running an experiment once that greatly depended on magnetic fields being exactly a specific way because they were looking at electron flow. But anyway, so if you change those electric fields, it changes the flow of those electrons. If you change how those electrons flow, it changes the result. And he didn't find that out until one day I was in the lab helping him with something, and we moved a helium container from one side of the really close to the apparatus to another part of the lab. And what it did was it actually messed with the magnetic field inside there because this big chunk of metal had kind of been moved, and that does have an impact on a magnetic field or electric field. It's all kind of related. Electric and magnetic fields are exactly related, but they're all related. So when you move a big hunk of metal, it screwed it up. And he was kind of happy that we figured that out because it actually helped him on something else. But had we not done that together, he might had I not gone on and just inadvertently moved his helium container, he might not have realized what the mistake was about to be that he was about to publish. So sometimes, it's nice to have other eyeballs. And the peer review process is a little more formal version of me helping a friend out in the lab. Okay. But sometimes the experienced scientists that are those peer reviewers can see gigantic holes you left in something like, hey, I tested this out and I got exactly this. Well, yeah, but if you go do, XYZ, it changes the complete result of this and you'll figure that out in that process. But I wanted to explain one of the things that scientists absolutely, I mean, this is our bread and butter in physics, and I'm a physicist, so I can only speak for us. But one of the things we do is we come up with theories, then we test them and retest them and test them in different situations and try them in different ways to see if it always works exactly the same, or if there's certain conditions under which it doesn't work or does work, in which case you don't really have a law, you have sort of an effect, which is a different thing. But here's an example of what happens. And I'm taking this from Carl Sagan. So one of the things in science we get to do is stand on the shoulders of giants. So I'm going to borrow an example from one of my scientific heroes. We're going to use his words. One of many examples of this is the laws of motion and the inverse square law of gravitation associated with the name of Isaac Newton, and they're properly considered among the crowning achievements of the human species. Now, this is me talking, not Carl. The inverse square law says the further away two objects are, the less gravitational impact they will have on each other. The further apart they are, it's actually the square of the distance in between the two. If they're far apart, there's almost no gravitational interaction. There still is one, but it's really small. So anyway, back to Carl. 300 years later, we use Newtonian dynamics to predict eclipses. Years after launch, billions of miles from Earth, with only tiny corrections from Einstein, a spacecraft can beautifully arrive at a predetermined point in orbit of a target world, just as plainly as the world comes ambling by. The accuracy is astonishing. Plainly, Newton knew what he was doing. And we've used gravitation. This is me talking now. We've used gravitational effects for things like Voyager to figure out how to get them close to certain things that we want them to see. And it works astonishingly well. I was just actually reading an article this morning, and Voyager's been up there a long time now. 50 years, a little bit more maybe. But Voyager is actually still sending messages back to Earth. The thing still works. But anyway, back to Carl. But scientists have not been content to leave well enough alone. They have persistently sought chinks in the Newtonian armor. For instance, at high speeds and strong gravities, Newtonian physics breaks down. See, it only works when you're at normal speeds and gravity that you and I are used to. Okay, back to Carl. This is one of the great findings of Albert Einstein's special and general relativity, and is one of the reasons his memory is so greatly honored. He disproved Newton. Einstein came along and said, hey, Newton, you got it right for the world you knew, but hey, for this new world, there's a whole bunch of new laws. And the fun part about Einstein's work is it applies to Newtonian stuff as well as other things. So let's go back to Carl. Newtonian physics is valid over a wide range of conditions, including those of everyday life. But in certain circumstances, highly unusual for human beings, we are not, after all, in the habit of traveling near light speed. It simply doesn't give the right answer. It does not conform to the observations of nature at those higher speeds. Okay, so that's important to know. It does form to the observations of nature until you get to those conditions. That's what Carl's trying to say. Now back to Carl. Special and general relativity are indistinguishable from Newtonian physics in the realm of its validity, but make very different predictions. Predictions is in excellent accord with observation in those other regimes. High speed, strong gravity. Newtonian physics turns out to be an approximation of the truth, good in certain circumstances, which we're all routinely familiar, really bad in others. It is a splendid and justly celebrated accomplishment of the human mind, but it has its limitations. And that's where Einstein comes in. Einstein came in and kind of formalized all this other world in other circumstances. So back to Carl. Scientists are today investigating regimes in which general relativity may break down. For instance, general relativity predicts a startling phenomena called gravity waves. Now, I want to point out, Carl wrote this a lot in the 90s. Since that point in time, gravity waves have not only been detected, somebody won the Nobel Prize for them. So if you're watching my Nobel Prize series, eventually we'll get to one on gravity waves. So that was actually proven. Back to Carl. He says they've never been detected directly, but they have been now. They weren't then. But if they do exist, there is something fundamentally, I misread that. I'm correcting myself. See, scientists are allowed to do that. Okay, so back to gravity waves. But they've never been detected directly. But if they do not exist, there is something fundamentally wrong with general relativity. Pulsars are rapidly rotating neutron stars whose flicker rates can now be measured to 15 decimal points. Two very dense pulsars in orbit around each other are predicted to radiate copious quantities of gravitational waves, which will in time slightly alter the orbits and rotation periods of those two stars. Now, Joseph Taylor and Russell Hulse of Princeton University have used this method to test the predictions of general relativity in a wholly novel way. For all they knew, these results were going to be inconsistent with general relativity, and they would have overturned one of the chief pillars of modern physics. Not only were they willing to challenge general relativity, but they were widely encouraged to do it. People were like, yes, go disprove it if you can. But here's the caveat. If you prove it wrong, you got to go figure out what takes its place. And that's the hard part. As it turns out, the observation of binary pulsars give precise verification of the predictions of general relativity. And for this, Taylor, and Hulse were co-recipients of the 1993 Nobel Prize in Physics. In diverse ways, now that's not the one for gravity waves. That's a future one that we'll get to, but this is sort of a secondary measurement of it. So long story, but if you watch my Nobel Prize videos, you'll see that explanation as I get to the more modern ones. We're about to launch the 1930 Nobel Prize, but we'll get to these pretty fast. So back to Carl. Nope. In diverse ways, many other physicists are testing general relativity. For instance, by attempting to, to, to directly to detect the elusive gravity waves. So like I said, that direct detection has now been done. This pulsar thing was a secondary detection, and there's a big difference in between those two things. One's a direct detection and one's a detect the effect of it. So it's sort of secondary. Okay, now back to Carl. They helped to strain the theory to the breaking point and discover whether a regime of nature exists in which Einstein's great advance and understanding turns out to be fall apart. If the general relativity is certainly an inadequate description of nature at the quantum level, but even if that were not the case, even if general relativity were everywhere and forever valid, what better way of convincing ourselves of its validity than a concerted effort to discover its failings and limitations? So there are spots in which general relativity doesn't quite work. So that's why you see all these articles about grand unified theory, string theory, quantum loop gravity, all kinds of other stuff. People are trying to figure out how to put those two things, put the rest of it together, because there are spots where it doesn't work, but doesn't say it's not great for what we know about, right? So that's how peer review is supposed to work. That's how science is supposed to work. We're supposed to challenge ourselves, and we're supposed to say, hey, look, Einstein, you weren't quite right in this spot. But you don't get to just walk up and go, hey, Einstein, you were wrong because I think. You have to go, hey, Einstein, I observed something that doesn't quite fit with your theory. That's how you disprove somebody. You don't just disprove somebody by saying, I don't agree with you, right? If I have a theory and I have an observation, it's a theory and an observation. And if people have repeated that observation and other people got the same answer, it's pretty hard it gets a little harder to dispute. Now, I'm all for trying to come back and tell scientists, hey, you don't quite have it right. But more and more what you see are people just going, well, I don't agree with that. They must have made it up. They must have lied. Well, sometimes science doesn't necessarily give us the answer we want. It gives us uncomfortable stuff. It says, hey, look, this thing you thought all along isn't quite right. It's actually wrong. Apologies for that, but it is what it is, right? You don't get to like it. It's the answer. So I do hope this helps understand how science is supposed to be done. I will be talking a lot more on these videos about both uh, uh, string theory and quantum loop gravity and trying to show where relativity falls apart. We'll be talking about relativity as well. And remember, I will keep the math at a bare minimum. If you want to talk about the math, please drop me a direct message and I will be happy to do a live stream with people, and we can actually go through math one-on-one or according to whatever live stream it looks like. But I will warn you, some of it gets pretty deep. So it's a little tricky math. It's pretty ugly stuff. But now that we have big computers to do the math for us, it's a little easier. So I do hope this helps clear up a few things about the peer review process and how it is that as a scientist, I feel we do truly get to stand on the shoulders of giants. Einstein got to stand on Newton. Everybody since Einstein is kind of standing on Einstein and still working through all the stuff he gave us. And someday there'll be somebody that comes along and says, hey, I figured out that's part that relativity doesn't cover. And then future generations will get to stand on top of him. So I hope everybody's enjoyed this video. I like doing them. Please check out our entire playlist on the Nobel Prizes. I've done the very first Nobel Prize up through 1929, and we will continue releasing those until we get to the very modern ones. And this year's Nobel Prize is going to be announced soon. I will do the prizes on chemistry and medicine and the other disciplines as well, but right now I'm going through physics. So I hope everybody has a great evening. Don't forget to click subscribe and like. It does help us out with the algorithms. Have a good one.